Chapter 7, Similar Polygons. Today we're going to cover Section 7.3, Similar Polygons. Your class opener, solve for x. So since you are solving proportions, you should be cross-multiplying. The objective for similar polygons. After studying this section, you'll be able to state and apply the properties of similar polygons. Similar polygons, they have the same shape, but not necessarily the same size. So if I even draw a shape, here's a pentagon. If I had an exact copy of it, they would be congruent. But similar just means it's the same relative shape, but it might be a different size. So the angles are still all the same, but now it's larger than before. So if I look at the properties here, it says corresponding angles are congruent, so all the angles still match up. Corresponding sides are in proportion. So maybe the one pentagon, everything is twice the size of the other one for the sides. And here's an example. So here's two hexagons that have the same shape. The angles all match up, but the sides are not the same length. And then we have a scale factor. It's the ratio formed by the lengths of two corresponding sides. So if I came up to the hexagons and I told you that the top of this one is 15 and the top of the other one was 10, and I asked for the scale factor would just be their ratio. So the scale factor would be 15 to 10, which I could then reduce to 3 to 2. So any of the other side lengths would have to be in the same ratio of 3 to 2. Tell whether the two polygons are always, sometimes, or never similar. So I'm looking for the angles are exactly the same and the sides are just all in proportion. Number 1, two equilateral triangles. So let's just draw two and see what happens. So here's two equilateral triangles. Would they be similar? Well, the angles are all going to match because any equilateral triangle is also equal angular, so the angles are always going to be 60. And the sides are always going to be in proportion. So if the one triangle on the right, if the bottom is twice as big, all the sides would be twice as big. So this is going to be in always. Number 2, two isosceles triangles. Well, for this one, if I'm thinking of two isosceles triangles, the first thing I sort of think of is if I have an isosceles triangle like this, I could get another one that's definitely similar to it, but I might get an isosceles triangle that is a shape like this where the angles aren't going to match up. So this one's just going to be a sometimes. Number 3, two squares. Well, I know for a square, no matter what I do, the angles are always going to be 90. So the angles will always match up. And I know every side in a square is the same. So if one side gets doubled, all the sides are going to get doubled. So it's always going to be in the same proportion. So a square is going to be always. Two regular hexagons. Now, one important thing about having a regular hexagon is if it's a regular hexagon, every single angle is going to have to be the same size. The other thing is all the sides are the same length. So if one side gets doubled, all the sides would have to get doubled. So this is another one that's going to be an always. A right triangle and an acute triangle. Well, right off the bat, I don't even need to draw this one. A right triangle has a right angle. An acute triangle, all the angles will be acute. So there is no way that all the angles can match up. So this is a never. Quadrilateral ABCD is similar to quadrilateral A prime, B prime, C prime, D prime. And we have some questions. Find the scale factor. So to get the scale factor, I really just need to find two corresponding sides, 50 and 30. So the scale factor will be 50 to 30, which I can then reduce and get 5 to 3. Find the values of AB, A prime, D prime, and B prime, C prime. All right, so let's first look at AB. I don't know how big AB is, but I know that the corresponding piece is 12. So the easiest thing for me to do is set up a proportion between those two values and then the two values that made up the scale factor. So I know my scale factor is 5 to 3. So I'm going to make up a proportion, and I'm just thinking the value for the larger quadrilateral goes on the top, which in this case I don't know how big AB is, so I'm just going to call it X. And then the value for the smaller quadrilateral goes on the bottom, which I noticed over here is the 12. And now just do a cross multiply. So if I cross multiply, I get 3 times X is 3X. 5 times 12 is going to give me 60. Divide by 3, and X equals 20. So I now know the value for AB, it's going to be 20. And I can even fill it in up here. Let's find the value now of the other pieces. So I'm looking for A prime, D prime. Okay, so I don't know that value, so I'll call it X. And if I look at what it corresponds to the side over here that's going to be 30. So I set up another proportion. And I'm always going to relate it to my scale factor. So my scale factor is 5 to 3. The number in the top represents the larger quadrilateral, which in this case is on the left over here, the 30. The number on the right is my smaller quadrilateral, which in this case is going to represent my X. And I cross multiply again. And notice I can't reduce between the 3 and the 30 because they're on opposite sides of the equal sign. So cross multiplying is going to give me 5X equals 90. Divide by 5, and you get 18. So I just found out that A prime D prime is 18. And the last one they want us to find out. Trying to find out B prime C prime, and I realized that it corresponds to BC, which is 22, and I set up another proportion. So my scale factor is 5 to 3. The larger quadrilateral value goes on the top, which is 22. The smaller on the bottom, which I'm going to call X, and I cross multiply again. So I get 5X equals 66. Divide by 5, and what do we get? 13 and 1/5. Looking at our last problem. Number 8, find the ratio of the perimeters. So if I go up to the original shapes and look for the values of the sides, I have 50, 30, 20, and 22. And if I add that up, I get 122. And then over on the right side, I have 30, 18, 12, and then the value of B prime, C prime, which we figured out down here was 13 and 1/5. So if I add those values up, I get 73 and 1/5. Okay. And now I need to try to reduce this ratio. So I really have two options. I can either turn the 73 and 1/5 into an improper fraction, multiply each side by 5 to get rid of the fractions and see if I can reduce that, or I'm going to actually just divide this out to a decimal and see what would happen. So I'm going to take 122 and divide it by 73, and I know 1/5 as a decimal is 0.2, and I get 1.6 repeating, which I really know is the same as 1 2/3. So let's see, so this is really the same as 1 2/3, but I can't have ratios as mixed numbers, so if I turn this back into a fraction, it's the same as 5/3, which would be 5 to 3. Now, here's something sort of interesting if you notice. So the ratio of the perimeters is 5 to 3, and notice that the scale factor back in number 6 is also 5 to 3. And this is going to happen for any problem. If you ever see a question where it asks, find the ratio of the perimeters, if you already know the scale factor for two sides, the ratio of the perimeters is going to be the same exact value. Number 10, triangle ABC is similar to triangle XYZ, and they have a scale factor of 5 to 3. If the perimeter of triangle ABC is 12, then the perimeter of triangle XYZ is what? And this is where I remember the scale factor for the sides is the same as the perimeter. So if I set up the scale factor as 5 to 3, that should be the same as the ratio of the perimeters, which is going to be 12 to x, I don't know. And now just cross multiply. So 5 times x is 5x, 3 times 12 is 36, divide each side by 5, and I get that x is 36/5 because it doesn't reduce. Or you could go to a mixed number if you wanted to and get 7 1/5. So the perimeter of XYZ is 7 1/5. And your closure. My worst experience with math was when